Hello again, physicists. It's good to be back. Today we are going to be going over atomic theory. So in electrostatics, we will be discussing how charge interacts with other charges. But first we need to understand, where is that charge located? Where is it coming from? So we're going to kind of do a review. You've probably done some atomic theory in a prior chemistry class or a prior physical science class, but it's always good to get a refresher. So several thousand years ago, Greek philosophers postulated that everything is made up of some sort of fundamental building block, which they called atomos. And this is where the first idea of the atom came from. And atoms are, at least as far as common matter goes, the most fundamental building block of everything. From you to your dog to the wind blowing outside, they're all made up of atoms. Now, this thought held true for hundreds of years, through many centuries, up until only about 125 years ago, where we began to detect that there are actually different charges inside of these atoms. And this was confirmed through the experiment conducted by one J.J. Thomson. And he changed the theory of an atom by saying now that we have two different types of charges inside of this atom, positive and negative charge, and that the negative charge is caused by something called the electron. And his model got us further towards the truth as to what the atom looks like, but not all the way there. So this is the first time where charge really came into the equation. But a problem with what Thomson had postulated was the fact that the electrons and the protons were mixed together, kind of like in a soup or a plum pudding, as he would call it. The next step was with Ernest Rutherford, not too much later than J.J. Thomson, where he, through an experiment, determined that actually the positive charge is separated from the negative charge. And the positive charge is focused in the middle of the atom, which we call the nucleus. And then the negative charge is arranged outside of that nucleus. So now we have a separation of that charge within the atom. Go just a couple years later, and one Mr. Niels Bohr went one step further and said that the negative charge is arranged in particular levels or orbits around that positive charge, that these were quantized energy levels, and that almost an atom looked like a small version of our solar system, where the nucleus would be like the sun, and then the negative charge, the electrons, are orbiting around that nucleus, like the planets orbit around the sun. And that worked very nicely for a couple of decades until we got to the quantum nature of subatomic particles like electrons. And the behavior of an electron is that it's not really necessarily in a discrete place, but instead we have to represent their positions using complex mathematical equations. And that's what the field of quantum mechanics is all about, applying these complicated mathematical equations to predict and determine the behavior of small particles like electrons. So these create orbitals which look somewhat like this, and you get these really goofy looking shapes that are representing the region in which individual electrons may exist, not one specific location. So that's kind of how we got to the model of the atom. Now, we will oftentimes use the Bohr model to show the charge within an atom just because it's a little easier to look at, even though technically speaking the quantum mechanical model is the true model of the atom. And it's going to be the protons and the electrons inside of atoms that will spawn all of the different discussions we will have when it comes to electrostatics. All right, so now that we're up to speed on what an atom is and the different charges that can exist inside of an atom, let's now compare and contrast them. So we have three subatomic particles of interest: the electron, the proton, and the neutron. I'm going to start with the neutron because it's going to be the most boring. The neutron has roughly the same mass as a proton, but it doesn't have any electrical charge. So when we deal with electrostatic forces and interactions, neutrons will not be a contributor. We will really never discuss them in our unit on electrostatics. However, our other two subatomic particles, the electron and proton, will definitely be part of our discussion. Now, we're going to compare and contrast the mass of both of those particles as well as their charges, because these two things will actually tell us something very important about electrostatics. The mass of an electron compared to the mass of a proton is somewhat smaller. In fact, the mass of an electron is approximately 1/2000th the mass of a proton. In other words, the mass of an electron is way, 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 way less than the mass of a proton. However, the charge of an electron compared to the charge of a proton, and we use the symbol lowercase q to represent charge in physics, those, as far as their magnitudes or absolute values are concerned, those are equal to one another. So in electrostatics, an electron will have just as much weight as a proton does, even though the electron has much less mass than the proton. The only difference between the charge of a mass and charge of a proton has to do with the sign on that charge. Electrons will carry negative charge, whereas a proton will carry positive charge. So the charges for protons and electrons are equal in magnitude, equal in size, opposite in sign. Now, what all this means is that because the charges are the same, but the masses are different, when we talk about charge being moved or transferred, it's going to be electrons that will do the majority of the moving, while protons will tend to stay stationary since they have about 2,000 times the mass of a proton. I mean, this is simple inertia here. The more inertia you have, the less you are able to be accelerated by forces. So since protons have more inertia, they have less of a tendency to be moved by electrostatic forces that we're going to study. All right, so the last thing will be how do we measure charge? And the answer is already on the screen. This right here is called a unit of a coulomb. And a coulomb is just an SI unit for charge. If you ever talked about charge or counted charge in chemistry, you used what's called an elementary charge. So that'll be our last topic for this video, getting from talking about charge as an elementary charge to talking it as a coulomb. Okay, so let's say that we have a lithium ion. So lithium is an element whose nucleus has 3 protons, and then if it was neutral, it would also have 3 electrons, but this is an ion, so it'll have an unequal amount of positive and negative charge. So 2 electrons, 3 protons. The question I want to know is, how much charge do we have here in terms of coulombs? So to determine that, I first need to figure out what is my net charge, because I'm going to get charged objects from having an imbalance of protons and electrons, as is the case here. So the first thing I'm going to do is I'm going to count up how many positive and negative elementary charges I have. In other words, how many protons and how many electrons do I have? I have 3 protons, each of which have a charge of +1. So if I'm going to determine my net charge in elementary charges, I'm going to have a +3, and then I also have 2 electrons. So I'm going to have 2 elementary charges that are negative. And to get my net charge, I will combine these 2 elementary charges. So in the end, this lithium ion has a net charge of +1, and that is elementary charge. The question is, how much charge do I have in coulombs? And to do that, I need to have a conversion factor. The conversion factor that we will use is that one elementary charge is the same thing as 1.6 times 10 to the minus 19 coulombs. In other words, it takes a lot of protons or a lot of electrons that are imbalanced to create just a single coulomb of charge. I can now use this conversion factor to figure out, well, what is the net charge on my lithium ion? So I would set it up like any other conversion problem. I'm trying to get rid of elementary charges, so that means that part of my conversion factor will go in the denominator. And I'm going to multiply that by the 1.6 times 10 to the minus 19 coulombs. So I do that multiplication, and elementary charges cancel out. And the charge on this lithium ion would be a positive 1.6 times 10 to the minus 19 coulombs. Very small amount of charge. And to really see an appreciable interaction between charged particles, you need to have quite a few of them, and they need to be unbalanced. You know, I can have a neutral object that has a lot of protons and a lot of electrons on them. But if I have an equal amount of each, it means I have no net charge. So that's it for new stuff for today. Just getting a basic understanding of where charge is coming from and how to count charge both in elementary charges and also in coulombs. So until next time, physicists, until next time.